as we get started with this next semester, we're continuing through our chapter on circles. So a lot of the things that you learned last semester, you have to still know. So as I've said before, you're not allowed to forget anything, even more true in the middle of a year. So things like, for instance, the distance around a circle is called the circumference. Any line that has its endpoints on a circle, chord. Any chord that passes through the center of a circle, diameter. A line that goes from the center of a circle to any point on the circle, radius. If two circles have equal radii or equal diameters, then the circles are congruent. In fact, that's how congruent circles are defined, is circles having equal radii or equal diameters. We said any limited portion of a circle is an arc. An arc exactly equal to half a circle. What type of chord would cut off a semicircle? Diameter would divide a circle into two equal semicircles. An arc that is greater than a semicircle, major arc. An arc less than a semicircle. If no arc is specified, we will assume, which one? Minor. You assume minor arc unless otherwise specified. So if you ever mean major arc in something, you need to make sure you indicate the major arc, usually by using a third letter, you'll recall. We said arcs in a circle will be equal to each other if, Audrey? Good, if their endpoints can be made to coincide. Could arcs in differing circles ever be equal to each other, Kendall? Only if, okay, she started to backtrack and then say, only if the circles are congruent. In non-congruent circles, can arcs ever be equal, Quentin? No. So a condition for equality of arcs, you must have congruent circles to begin with, otherwise the arcs could not be equal. We talked about different ways to prove that arcs in the same circle or in congruent circles would be equal. Ethan, one of those ways to prove that two arcs are equal in the same circle or congruent circles. Subtend them are equal. Okay, yeah, if we have two equal chords in that circle or in those congruent circles, then the arcs that they subtend have to be equal. Another way, Jamie?
I'm not sure.
If two congruent circles or the same circle have two equal chords, they will have subtend equal arcs. We could also get equal arcs, Genesis, if we had Chris? Equal central angles, right? If you have two equal central angles in the same circle or congruent circles, they will intercept equal arcs. What is a central angle anyway, Genesis? Angle that's central? Right. But for it to be central, what kind of lines would form a central angle? That's actually true because they would be radii. There we go. Right. Two radii would make the central angles. What if I wanted to show that one arc is greater than another arc? How might I show that?
The central angle is larger.
Good. A larger central angle would intercept the larger arc. Similarly, if I wanted to show that, what's the other way I could show that one arc is greater than another? Audrey? Greater chord, right? Greater chord would subtend rather a greater arc as well. What if I wanted to get two central angles to be equal to each other? Kendall? I wanted to show that two central angles have to be equal. One way to do it. If their arcs are equal, then the central angles have to be equal. What if I want to get a couple chords equal to each other in the same circle or congruent circle, of course? Chris? Equal arcs. If I wanted to get two unequal central angles in the same circle or congruent circles, back to Quentin. Unequal arcs, or two unequal chords in the same circle or congruent circles. Unequal arcs, right? So arcs, chords, arcs, angles are all tied together, remember? We also said this, that the largest chord which may be drawn in a circle, class, is the diameter. But we said this as well then, that as a chord gets further from the center, that chord will get, class, smaller. so that the nearer the center a chord gets, it gets larger, so that at its largest, it is actually through the center. If two chords are the same distance from the center class, then they'll be equal. Again, that's in the same circle or in congruent circles. We said that if you were to draw a polygon completely consisting of chords, so that all the vertices of the polygon lie on the circle, we would say that that polygon is, anyone? Inscribed. Kind of picturing chords inside the circle, vertices on the circle. That would be an inscribed polygon. The circle, then, we would describe as being circumscribed about the polygon. All right, that's all review. That's all stuff we should have known. Terms definition section of your notebook. Let's get into some new notes. So hopefully the brains are firing now, and we are shaking off the rust of Christmas break and 2 weeks of junk food and good food and generally lots of food. I know, I love food. I love food and football. Christmas break is awesome. Lots of good food, lots of football.
Lots of Browns beating the Steelers.
Oh.
Did you see the Ravens game? They pulled it.
Did you see Tom Brady threw 4,500 passing yards, 47 touchdowns, and only 12 picks?
Yeah. Anyway,
I
don't hate him as bad now that he's not on the Patriots. All right, terms definition section of notes. We've said before that if you have a circle, a line can intersect the circle at how many points, class?
1, 2.
2. A line can intersect the circle at no more than, I guess it would have been a better way to word it, no more than 2 points. But we also understand that a line could totally miss the circle, and we also said that a line could be drawn in such a way that it just touches the circle at 1 point. This is the line we want to look at here in your notes, terms definition section. Go and write this term down. Tangent. Tangent. A tangent is a line that intersects a circle at only 1 point. A line that intersects a circle at only 1 point. Now, you've heard the phrase going off on a tangent. How many have heard that phrase before? It's kind of like going off on a rabbit trail is another example, where you're talking about something, and something in that conversation triggers a thought that takes you over here that has nothing whatsoever to do with it. The only point in common was that initial thought, and from there, nothing else matched up with what you had been talking about. Here's the point in common, and it just goes off further and further from the main topic as you go, okay? So a picture of going off on a tangent, that's actually where the phrase comes from. It's a mathematical phrase. You now feel smarter for having learned that. So a tangent is a line that intersects a circle at only 1 point. The point at which it intersects the circle is called the point of tangency. That makes perfect logical sense, right? Point of tangency. Mathematicians are not particularly creative. We've got a tangent here. What do we call this point where it's tangent? Why not point of tangency? Very good. So the point of tangency is the point at which a tangent touches a circle. The point at which a tangent touches a circle. Call it the point of tangency.
Is there a shorthand for tangent?
There is not, but it's not a particularly long word, so no. Now, if you imagine for a moment, if I were to pick another point of tangency, I could draw that, and maybe pick another point of tangency, and maybe I could draw that, and maybe another point of tangency, and maybe I could draw something like that, and maybe another point of tangency, and draw something like that. And what you see here is if I were to call this A, B, C, D, E, notice that A, B, B, C, C, D, D, E, and EA all are tangents to the circle, right? If you have a polygon, all of whose sides are tangent, notice now the polygon is on the outside. So we refer to this as a circumscribed polygon. We've been unable to define this term in the past because we didn't know the term tangent. But now that we've defined what a tangent is, we can finally describe the circumscribed polygon. It is a polygon, all of whose sides are tangent to the same circle. A polygon, all of whose sides are tangent to the same circle. A circumscribed polygon. And then an inscribed circle then would be the circle inside the circumscribed polygon. So the circle is inscribed when the polygon is circumscribed around it. An inscribed circle, circle within a circumscribed polygon. Questions on these terms? Pretty straightforward. Just a new term for you to know, tangent. Tangent touches a circle at only one point. Now that's the definition of tangent, right? But there's a clang response to tangent that I want you to think of. Because the fact that a tangent touches a circle at one point doesn't do a whole lot for you in a proof. But this next theorem will. Remember with parallelograms, the very first theorem was clang, all the sides are equal, all the opposite angles are equal. Right? Opposite sides equal, opposite angles equal. And it was almost like definition of parallelogram, except it wasn't, right? But every time we had a parallelogram, by definition, sides are parallel, and opposite sides are equal, opposite angles are equal. It was that important. It was a clang response. Well, with a tangent, we're really not going to use the definition, touches a circle at one point very often. But Theorem 39 in your Theorems Corollary section of your notebook is our clang response. Anytime you see a tangent in a given, clang, you're going to think the word perpendicular. Theorem 39. Theorem 39 in your notebook says this: a tangent to a circle, is perpendicular. A tangent to a circle is perpendicular to the radius or diameter drawn to the point of tangency. A tangent to a circle is perpendicular to the radius or diameter drawn to the point of tangency. A tangent to a circle is perpendicular to the radius, to the radius or diameter drawn to the point of tangency. Once you have that down, turn to the proofs section of your notebook, proofs of theorems corollaries, and on a new sheet of paper at the top of the page, put Theorem 39, and just kind of quickly get this shorthand idea down that a tangent perpendicular to radius or diameter. Tangent perpendicular to radius or diameter. The clang to tangent is going to be perpendicular. But let's prove that that is so. Can't have you just believe in everything I say. How many of your parents watch the news? I'm just curious. How many of your parents, as they watch the news, like, how many of you watch the news? Any of you actually? Okay. How many of you, as you're watching the news, like, you've gotten to the point now where you believe nothing that is said? Like, they say something, you're like, yeah, right. Like, and it doesn't matter which place you're watching, like, really? Yeah, prove it. I don't know. It's just so bad, right? How many of you are that way in this class? I'm like, I say this is true, and you're like, yeah, prove it. Okay, not everyone. Okay. Anyway, Theorem 39, we're going to prove it. That a tangent is perpendicular to a radius or diameter drawn to the point of tangency. On your paper, go ahead and draw a circle to the best of your ability. If you want to cheat and use a compass, you can, but that takes too long and I'm lazy. So I'm just going to draw a somewhat circular looking thing. Go ahead and call it circle O. And this is the fun part, is trying to draw a straight line that approximately touches at just the one point. Now with a straight edge, it's not too bad. We're going to try to freehand a line that we think will touch the circle at only one point. And we'll call this point A. Go ahead and call your tangent line MN. Now the good news is we don't trust our eyes, so we're going to be given that it really is tangent regardless of how it looks. Because it can be a bit of a challenge to draw a tangent line. How many say, yeah, mine didn't turn out so good? Anyone say, I actually did really good.
I'm probably Picasso.
All right, so we got some Picassos in here. Okay, good. All right, so we also want to draw then this radius to the point of tangency. We understand that from the center of the circle, which is a predefined point, to the point of tangency, which must also be a defined point, only one straight line may be drawn. So there is only one radius that can be drawn to this tangent. We want to prove that that radius then is perpendicular to the tangent. For our given, we're given circle O with tangent MN, tangent at A, and we're also given radius OA. So given the circle with a tangent, the tangent is tangent at A, and we've got a radius from O to A. we're seeking to prove that a tangent is perpendicular to this radius, or diameter if I've drawn it all the way through to another point. So we want to prove that MN is perpendicular to OA. We'll prove that MN is perpendicular to OA. Now I will say this is a very hard proof to put together if you try to do it formally, directly. So we're going to do it indirectly. Do you remember indirect proof? It's been a little while. What's the basic idea behind an indirect proof, Ethan?
Proving that it's true, or not true, or something like that, or something.
Proving that it's not true, okay?
Not
You begin by assuming, class, the opposite, good Jamie, of what we're trying to prove, and then show that that assumption is impossible, ridiculous, absurd. Okay, so we're not going to put statements and reasons because we're not going to be able to have a reason for our assumption. It's just an assumption. But we'll still start by numbering our statements. So down below, statement number 1, we'll still start with our given. We know we've got a circle. We've got a tangent, a line that touches at one and only one point. We're told that this point is called A. And we're given the radius to the tangent. After the given, number 2, what should I write for my assumption? Quentin? Chris, help?
MN is perpendicular to OA.
Well, we want to begin by assuming the
Oh, it's unequal.
opposite. So we're going to say assume MN is not perpendicular to OA. Very straightforward. We're going to assume that MN is not perpendicular to OA. We're trying to prove that it is. Let's start by assuming it's not. And let's see what the implications are. If we assume if this is not perpendicular, then what's the fallout of that? Let's show that the fallout is impossible. Well, if MN is not perpendicular to OA, then you understand that there is some other line from this point that would be perpendicular, correct? If OA ain't it, then it's somebody else, right? So let's go ahead and draw another line here. OB. And let's go ahead and say number 3, draw OB perpendicular to MN. Since OA we are assuming not perpendicular, then we should be able to draw another line that is. So let's draw OB. So it's perpendicular to MN. Now, question for you. Where is B in relation to the circle?
outside of it.
Is it inside, on, or outside?
Outside.
It must lie outside, because remember, we had previously stated that any line, in fact, it was one of your circle properties, that any line that goes through a point inside the circle would intersect the circle at 2 points, right? Entry wound, exit wound, okay? So therefore, B cannot be inside the circle, for if it were, this would no longer be a tangent. It would not touch at 1 point, but rather 2, right? So B can't be inside the circle. B also cannot be on the circle, because otherwise now this line is still touching the circle at 2 points. So we can state conclusively then, based on those circle properties, what we know of circles, B must lie outside circle O. Correct? And it looks that way in our picture anyway, but we don't really trust our eyes. We're stating, no, it not only looks like it's outside the circle, it has to be outside the circle, correct? Now, we had also stated that a point lies within, on, or without a circle, according as its distance from the center is less than, equal to, or greater than the radius, correct? So if a point lies outside the circle, that point's distance to the center must be greater than the radius, correct? OA is a radius. B lies outside. So the distance from O to B, which would be the line OB, has to be greater than OA, correct?
Correct.
Do we follow the logic there? So OB, then, because B lies outside the circle, OB must be greater than OA. Now, there's another way in which you could actually go about proving that. We'd established enough other things in circle properties we didn't need to, but we could have labeled this point here C or something, the point where it crosses. Because if B is outside, then that means that from O, it must cross the circle at some point, maybe call it C. And we know that the whole is greater than any of its parts, so OB must be bigger than OC. Since OC and OA are equal radii in the same circle, then by substitution, OB is greater than OA. So there's a couple ways you could go about this, but I feel with the circle properties we had discussed, by stating B is outside the circle, that tells you OB has to be bigger than OA. Now, question for you. If OB is the perpendicular, Kendall, what do we know about the perpendicular from a point to a line? It's always she forgot how I work over Christmas break, didn't she? Class, OB has to be the shortest line, because it's the perpendicular, right? We've previously proven the shortest line from any point to a line is always the perpendicular. So if OB is the perpendicular from O to MN, OB must be less than any other line from O to MN. Well, what other line do we have from O to MN, class? OA. So OB must be less than OA. Wait a second. OB can't be bigger and smaller at the same time. That's ridiculous. What caused this inconsistency?
Because B is outside.
The assumption. Our assumption then must have been flawed. For us to arrive at a contradiction means the assumption was flawed, because everything else had geometry, logic, reason. This just didn't have the reason for it. So therefore our assumption must be wrong, and if the assumption is wrong, that MN is not perpendicular, then MN must in fact be perpendicular. Questions on this indirect proof? Had a funny look on face. Did you process all
I'm
that?
just not good at indirect proofs.
Indirect proof is not that
You just work to a contradiction. Again, I'm not going to ask you to do one of these on your own. I would always guide you through them. What?
I guess we just don't do them enough.
We don't do them often. They're really just for establishing hard to prove concepts that directly would be a challenge, but indirect is like, oh, well, yeah, if you assume MN's not perpendicular, if you assume that this isn't the perpendicular and that something else is, well, that doesn't make sense.
I would have been stuck on this for like 2 hours. And still not.
All right, do we at least understand that proof now? Even if you say, I could not have come up with it, do you at least understand it? Question?
So you said there was a way to prove it, just it was hard.
There probably is. I'm just not I don't know how exactly you go about proving conclusively that it absolutely, like, how do you prove there's a right angle there? That's so challenging. So this is much easier, and I'm lazy, and I like the easy way. All right, so the key here is your clang. Tangent, think clang, perpendicular to a radius. All right, corollary 39-1. Going back to the theorem's corollary section. Corollary 39-1. What are the implications of this? If we've now established that a tangent is perpendicular to a radius or diameter at the point of tangency, then what else must immediately follow in corollary fashion?
It must bisect.
So corollary 39-1, a straight line perpendicular to a radius or diameter, a straight line perpendicular to a radius or diameter at its endpoint on the circle, a straight line perpendicular to a radius or diameter at its endpoint on the circle is tangent to the circle. A straight line perpendicular to a radius or diameter at its endpoint on the circle is a tangent to the circle. A straight line perpendicular to a radius or diameter at its endpoint on the circle is tangent to the circle. We're not going to do the formal proof here, but just talking it through. You've got a radius of a circle. At the endpoint on the circle, you draw a perpendicular. If you draw a perpendicular, it's got to be tangent. Why? Well, again, we just proved that if you have a tangent, it will be perpendicular to the radius. So if you have a radius that is perpendicular, then it must be a tangent, right? And again, you would assume the opposite and show that that falls apart immediately. That would be a very short indirect proof. So if it's tangent, it's perpendicular. If it's perpendicular at the end point, it's tangent. Does that make sense? So that converse idea. Corollary 39-2. Corollary 39-2. A perpendicular to a tangent. A perpendicular to a tangent at the point of tangency. A perpendicular to a tangent at the point of tangency passes through the center of the circle. A perpendicular to a tangent at the point of tangency passes through the center of the circle. This one is not quite as useful to you because it's hard to draw a tangent, but if you somehow drew a tangent line, found the point of tangency, and then constructed the perpendicular, the center of the circle is going to be on this line. Why? Because what is a tangent perpendicular to? A radius or diameter. So if you were to draw this, that must be the diameter if it's really perpendicular, and therefore the center of the circle would be the midpoint there. So you could locate the center of a circle by drawing any tangent, which is hard to draw in the first place. But if you drew it perfectly, a perpendicular at that point, and then bisecting that would give you the center of the circle. Corollary 39, question first.
Yeah. So if you were to draw the same exact tangent line on the other side of the circle, that would be parallel and equal, right?
What do you mean by equal?
It would be parallel?
Right, good observation. So we're actually going to put this in our class notes in a minute. If you were to have a diameter and you drew tangents at opposite ends, because they're both perpendicular to the same line, they are parallel to each other.
Does it have to be a polygon? Like with tangents, like we said, like
a polygon?
Or oh.
I mean, if you wanted to draw another tangent line or something here,
oh, I see what you mean.
you could make a polygon with these tangents, but
I got my definitions mixed up.
right. Mainly this corollary that was just emphasizing a singular tangent. The perpendicular at the point of tangency will always go through the center. It'll be a radius, diameter, or extended further. Corollary 39-3. The perpendicular drawn from the center of a circle, the perpendicular drawn from the center of a circle to a tangent, the perpendicular drawn from the center of a circle to a tangent passes through the point of tangency. There's only one perpendicular you can draw, and so if it's going to be perpendicular to the point of tangency, then your perpendicular must go through the point of tangency. The perpendicular drawn from the center of a circle to a tangent passes through the point of tangency. All right, questions on those corollaries? So you see a continual word that keeps coming up every time we talk about a tangent class. What's that clang word? Perpendicular.
Oh.
Tangent, think perpendicular. Perpendicular to what class? Radius or diameter. And if radius or diameter is perpendicular at the end point, then it must be a tangent. Class notes section of your notebook. Class notes section of your notebook. Here's some statements down. These are not theorems corollaries, but they're all very important statements that you need to have memorized. So I'm going to put these in the class notes section of your notebook now. First thing I want you to write down is this. At a given point on a circle, at a given point on a circle, only one tangent may be drawn. At a given point on a circle, only one tangent may be drawn. Let's think about this. We have a circle. We pick a random point. I'm saying there's only one tangent you can put right there. Why couldn't you put more than one? How would we prove? We're not going to do the proof for sake of time, but thoughts on how we prove you can only have one tangent right there. Why not another tangent or even a third tangent? How come only one line can be tangent there? Thoughts?
Does it have to be a straight line? No, they're all straight lines. Because they would pass through different parts of the angle like in which they're like drawn. Like, wouldn't they pass through different parts?
Would they?
No,
I'm pretty sure they would.
only one point can be shown that, only one straight line can be drawn through again.
How many straight lines can you draw through a given point, class?
Infinite.
Infinite number. You can draw an infinite number of lines through this point, but this idea that I had you write down says only one of them can actually be tangent. Why would that be?
The definition of a tangent is line that intersects a circle at one point. So
Yeah, but how do I know that this one point isn't the same for all three of these different lines?
There's only one tangent can be drawn through that one point.
Well, that's what I'm telling you. How would we prove it? What's the key word to tangent, class?
Perpendicular.
Perpendicular. So what if we did have a perpendicular? Where would that perpendicular go, class? To the center of the circle, right? Now, question. This is a straight line. This is a point in this straight line. How many perpendiculars can you draw to a line at a given point? One. So because we've already established you can only have one perpendicular at a point in a line, therefore only one tangent can be drawn. Any other line that looks tangent can't truly be tangent. Only one line can actually be tangent. Now the hard part is when you freehand a circle, you don't have perfect curvature, right? Sometimes it smushes a little bit, and so it looks like you can get more lines through, but you can only actually have a single tangent at a given point. Okay, so there's one thing I want you to write down. Here's another thing I'd like you to write down, something Chris actually mentioned a moment ago, that tangents to a circle at the end points of a diameter, tangents to a circle at the ends of a diameter are parallel. Tangents to a circle at the end points of a diameter are parallel. And we actually already addressed why this must be. You have circle or badly deformed egg. You draw a diameter. You put a tangent here. You put a tangent here. It kind of looks like not a TIE fighter. Yeah, TIE fighter, right? That's the ones for, yeah. Anyway, but why must they be parallel? Not just because they look parallel. Why must they be parallel? Chris, do you remember what we said?
Because the diameter is two radii put together in a group. They both bisect radii and all radii.
There's a key word to tangent, Chris. What's the key word? Perpendicular. Okay, listen, class. When I talk about claim statements, that's what you come back to every time. In proofs, right? You see that claim statement. Come back to that every time, right? Use that every time. You see, for instance, parallelogram. Get your parallel lines, get your equal lines every time. Come back to that. You get, a transversal and parallel lines. Get your corresponding angles, the alternating angle. You see perpendicular. Get your right angles. You see bisector. Get those equal pieces. Use here tangent, clang, perpendicular. Okay, so now that we've established perpendicular, Chris, why are they parallel to each other?
Because only one perpendicular can be drawn from 2 points.
Perpendicular to the same line.
Two lines perpendicular to the same line are parallel to each other. Okay, so that would be the proof of that one there. Let's see, next statement I want you to write down. It says, if two tangents to a circle meet in a point, if two tangents to a circle meet at a point, meaning they're not at the end points of a diameter, okay? These two tangents will never intersect. So what we've got instead is maybe a tangent like that and a tangent like that, and they meet at a point. Okay, so it's like Death Star blowing something up. All right, so if you've got two tangents to a circle and they're meeting at a point, that's what we've got here. They're not parallel to each other. They're not at the ends of a diameter. If two tangents to a circle meet at a point, the center of the circle is in the angle bisector of the included angle. The center of the circle is in the bisector of the included angle. The center of the circle is in the bisector of the included angle. If two tangents to a circle meet at a point, the center of the circle is in the bisector of the included angle. How would we prove that this line, because of course we know 2 points determine a straight line, correct? How would we prove that this line then bisects this angle? Because it doesn't look like it does. It looks like it's got a big angle and a littler angle.
From one point they're equidistant. Sides, so because any point on an angle bisector are equal lines.
If a point is equidistant from the sides of an angle, then it lies in the angle bisector, right? Okay. So in other words, Chris, you're saying if I can show that this point is the same distance to this line as it is to this line, then it's got to be the angle bisector.
Well, I mean, it would be, because angle bisectors, well, they would be the same line. Even though all radii are equal, so it would be the same distance.
Oh, yeah, if we were to draw radii to the points of tangency, we know that all radii are equal, correct? And what is the distance from a point to a line, class? The perpendicular. So since the radius is perpendicular, it is the distance. Since this is a perpendicular, it's the distance. And since all radii are equal, this point is equidistant. Yes, it must lie in the angle bisector. Make sense? Questions on that one? Yes, sir.
So if you see a bisector in a circle, are you supposed to think tangent? Like if you see a bisector in a circle, but no tangent is drawn, are you supposed to assume it's tangent?
No. Bisector does not imply tangent.
Not bisector, perpendicular.
Oh, if you see perpendicular.
Yeah.
Only if you've got a perpendicular at an end point. For instance, if you have a circle and you've got two lines that are perpendicular, they're not perpendicular at an end point, correct? And furthermore, it's not radius or diameter, but a radius or diameter, and at an end point on the circle you've got a perpendicular? Yeah, absolutely.
I don't think that will really help.
That's Clang. It has to be a tangent for, I think, corollary 39.1. So, yep. All right. You don't have to do this one necessarily in the class notes section, though you're already there. I want to do a proof with you now that uses tangents, so we kind of get a feel for how to use tangents in proofs. So if you want to go and draw a circle on another sheet of paper, or you could perhaps use that same paper you've been on, though this doesn't necessarily have to do with those same statements. Go and draw a circle. And let's go ahead and call it circle O, just because we're boring like that. And once again, let's go ahead and draw a couple of, well, let's start with one tangent. Let's start with one tangent. So a line that, to the best of your ability, touches at only one point. And if you miss like I did, make it up. Okay, that's where it touches. That's the point of tangency. All right. And then somewhere along the line here, and you can make it a longer line, I suppose, if you wanted to. You can make it as long as you want. Pick some random other point in the line. Let's call the point of tangency T for tangent. And let's pick another point down here. Let's just call it P for point. So pick some other random point. Call it P. Now, from this point, there are an infinite number of lines that you could draw, correct? But what I would want you to picture here, and if you wanted to, I guess you could get your compass out and do this. I want you to imagine this length. And I want you to imagine tracking it off down here. So that this distance marked off to some point here on the circle, horrible, is equal. And just call this point A. So we're going to measure this distance and mark it off to the circle so that PA and PT are equal to each other. Now, you could, of course, extend this line further if you wanted to, but we're going to call this point A. Now, based on how I have my line drawn, and it's not measured and we don't trust our eyes, does my line PA extended appear to be a tangent?
No.
No. It looks like it just cuts through the circle at a second point, right? It's close to a tangent. We're going to prove that it should have been. That if I were a better artist, or if I'd done this with measuring it out, in fact, suppose if you wanted to, go and get your compass out. If you have it with you, don't have it with you, it's not the end of the world today, but if you have your compass with you, go ahead and get it out. That might actually help here to draw a circle. Always good to have it in class, by the way, so a reminder, always have it with you. You never know when we're going to do something. So if you have your compass, go and draw a circle. Let's do it this way. The rest of you just kind of watch as I do it here. You know, we're limited by our own artistry ability. We can see here this would not be a tangent, but as I come up closer, I get to the point where I'm right at the edge of the circle. Okay, now I've got pretty much the tangent. And we pick some random point. Okay, so here's the same picture, but actually done with proper tools. It's an actual real circle instead of whatever that is. And then again, we take this measurement of PT, because remember a compass is used to measure a line segment, and we measure from that point to the circle, to a point we'll call A. Now if you were to connect it, here's the question, do you actually get a tangent?
Yes.
It appears that we do. Now again, my drawing didn't look like it did, but you can see it a little bit better here. We're going to prove that it really does have to be a tangent line. So when you're given circle O, we're going to go back to the flawed drawing though, since not all of you have the ability to make the perfect drawing. We're given circle O with PT tangent at T. Circle O with PT tangent at T. A is a point on circle O such that PA equals PT. A is a point on circle O such that PA equals PT. We want to prove that PA is tangent to circle O. We want to prove that PA is tangent to circle O. Let's get that down in 2 columns, statements, reasons. Once you got that down, 2 columns, statements, reasons. Get down your first statement and your first reason. We have only one claim word, class. Tangent. And what's the claim response to tangent?
Perpendicular.
Perpendicular. What is a tangent perpendicular to, class? No. Radius or diameter. Okay, center of a circle is a point. You can't have perpendicular to a point. But yeah, it's perpendicular radius or diameter through the center of the circle. Only problem is I ain't got no radius or radii or diameters, so I can't say nothing about it. Oh, draw them. That's a great idea. So let's go ahead and draw OT. Or TO, draw TO. Reason?
2 points determine a straight line.
Right. Good. When he said draw TO, I knew exactly what he meant. 2 points determine a straight line.
Draw OA.
You want to go and get OA in there as well? Why not? Now, I don't know that PA is a tangent. I'm trying to prove it is, right? So I can't assume that this is perpendicular, but do you see the idea of this proof? If it is perpendicular, then it's a tangent. So the idea of proof is I know this is tangent, so I know this is going to be perpendicular. If this is perpendicular, then this will be tangent. Do we see it? That's going to be kind of our method here. So let's also draw OA.
I have a question.
Draw TO and OA. Yes, sir.
So if you prove, we may have just said this, but if we prove OA is a radius, then that would prove that P.
Well, OA is definitely a radius because it goes from the center to any point on the circle. It just doesn't appear that I have a right angle here. Do you see it? It doesn't look like a right angle. If it were a right angle, we had proven that if a line is perpendicular to a radius, then it's tangent. So we're going to try to prove that despite what it looks like, that has to be a right angle. Okay. All right, so we drew our 2 radii, and that kind of presents a claim in itself.
They're equal.
They're equal. So number 3.
OT equals OA.
Reason?
All radii in the circle are equal.
Good. And I like that Quentin, you threw in there in a circle. I heard that from Ethan as well. I heard it from Quentin first. All radii in a circle are equal. Not all radii are equal, only if they're in the same circle or in congruent circles. In this case, they are. Now back to the original claim though. The original claim was claim, we have a tangent. So claim, class, we have perpendicular. We just didn't have a radius yet. Well, now we have a radius, so let's go and state number 4, Genesis, that remember, if PT is a tangent, clang, so therefore, to TP, yes, okay. OT is perpendicular to TP. Has to be perpendicular because, here's your clang statement, a tangent is perpendicular to a radius or diameter, but I'm not going to write that because I'm lazy. Tangent is perpendicular to radius at the point of tangency. Of course, a tangent isn't perpendicular to all radii, only the one that goes to the point of tangency. So tangent is perpendicular to radius at the point of tangency. Well, that presents another clang, because if OT is perpendicular, Kendall, clang, we have a right angle. So number 5, we can state that I'm sorry? Do we know that there's a perpendicular here? No, because we don't know that this is tangent. We only know this one's tangent. We're actually trying to prove this one is. We know this is tangent, so we know there's a perpendicular, so we know that's the right angle. Does that make sense? So number 5, we should state, or maybe better, OTP, right? Angle OTP, or maybe number it, angle 1, because technically there's 2 angle T's, and technically they are both right angles, but you have to say angles T are right angles, and that's just awkward. So angle OTP is a right angle. Reason? Good definition of perpendicular lines. So I've got this right angle. Okay, all of that's just kind of clang, right? Now, that's how we start every proof, is get all your clang. Now let's transition. How do we want to prove this? I want to prove this is a tangent. In order to get it to be a tangent, class, I need to have a perpendicular. So understand, if I can get OA perpendicular to PA, then I've got my proof. That's the essence of the analytic method. What one thing would you have to prove to get that? It's where Trump's lawyers are right now. What one thing do we have to prove to get the election overturned? The problem is they can't seem to figure out what that one thing is, or they just can't prove that one thing. Okay? But that's the essence of the analytic method. I want to prove PA's tangent. What one thing must be true? OA has to be perpendicular. How do I get OA perpendicular? What would cause there to be a perpendicularness? A right angle. So do we understand that if angle A, or angle OAP, is a right angle, then we do have a perpendicular, and then we do have tangent. Okay, this is again analytic method. How do I get a right angle right there?
Equal, wait, this may be in a triangle, but is it equal lines means equal angles, or equal sides? Oh, equal sides in a triangle means equal angles. Right,
in a triangle. And here I do have 2 equal lines, but I've got a weird quadrilateral thing.
Draw OP.
Draw OP? Okay, Ethan, let me stay on you on this. What would drawing OP do for me?
Form 2 triangles.
Okay, it would form 2 triangles. Sorry, I have these marked as equal and those the same marking, so these are equal separately. You would get 2 triangles. Okay, your thought of 2 triangles is what?
Congruent triangles.
Okay, so you're saying if these 2 triangles were congruent, that would get me a right angle?
Well, that other angle is already a right angle.
Stay with me. Okay, so you're saying that if these are congruent, that because this is a right angle, this corresponding part would have to be a right
It's
angle.
already congruent.
They're already congruent. What do you mean they're already congruent?
Side, side. OP equals BO.
Oh, okay, so, class, did you follow what he just said? We go ahead and draw OP as well up in number 2. Go and work that in there as well. And we know number 6, that OP equals OP by class identity. Oh, so look at that, we're back to congruent triangles again. And therefore, I've got these lines equal, these lines given equal, this line equal to itself by identity. Class, I do have 2 triangles that are in fact congruent by, so we could say that triangle top is congruent to triangle AOP, by side, side, side. And if that's true, then the angle OTP is equal to angle OAP by CPCTE, which means because angle OTP was a right angle, number 9, that means that angle OAP must also be a right angle by, I'm sorry? CPCTE. These two angles are equal by CPCTE, and since this is a right angle and these are equal, then this is a right angle by substitution, right? We're substituting OAP right there where it says OTP. It's just a substitution with a sound effect. Because let's face it, life's better with sound effects. And if I've got a right angle, then these two lines, despite their appearance, must be perpendicular. Number 10, OA really is perpendicular to PA despite the horrible drawing I did. How do I know it's perpendicular?
Right angle.
Definition of perpendicular lines, right? We have a right angle. What kind of lines form right angles? Perpendicular lines. The definition of perpendicular lines. And so, if you have a perpendicular to a tangent at its endpoint on the circle, you have a, if you have a tangent to a radius, at the endpoint you have a tangent, corollary 39.1. So yes, number 11, PA is tangent to circle O, because if a line is perpendicular to a radius, you're dismissed, Brecken. If a line is perpendicular to a radius at its endpoint on the circle, if a line is perpendicular to a radius at its endpoint on the circle, then it is tangent to the circle. If it's tangent, clang, perpendicular, yes, but if it's perpendicular at the endpoint, then clang, tangent. All right, there we go. No homework this evening other than take some time in study hall, at home, read through your notebook again, just very quickly, refresh your memory on this stuff. Not just the stuff we talked about today, the stuff from all year, because you're going to have to know it and continue to use it. Refresh your memory tonight. Don't wait. Otherwise, life gets harder. You are dismissed. Have a wonderful rest of your day.